is sometimes when you look at these, we're this is considering metathesis reactions here, but sometimes there's potential for other reactions to occur as well. And so when you start to go through, and the more reactions you see, the more familiar you're going to get with chemical properties. So if somebody asks you, what are the chemical properties of potassium ions, what would you say? For example, in potassium sulfide, you got potassium ions and sulfide ions. And so sulfide ions, what's the formula for sulfide? S2 minus. All right, so let's look at potassium ions first. What are the chemical properties of potassium ions? Well, then you'd think, how many chemical properties are there? How many chemical properties are we going to consider? 3. And so what are they?
Redox, acid base.
Redox, acid base, and metathesis. And so when we look at potassium ions, well, first off, we've talked about metathesis. Well, what other ions does potassium like to react with? What ions is, okay, so when I ask about metathesis reactions, you're looking for precipitation, gas formation, and stronger to weaker acid. And so those types of things. So what ions does potassium ions precipitate with? What anions? Nothing. And so it's very unreactive. Potassium ions are very unreactive in terms of metathesis. They aren't going to precipitate out with anything. They aren't going to combine with anything to form a gas, and they aren't going from a stronger acid. Is potassium ion a good acid or a base? Not really. And so these are considered neutral. For example, if you wanted to increase your stomach acidity or decrease your stomach acidity, you wouldn't take potassium necessarily. I mean, it'd have other effects. All right, so potassium ions are unreactive metathesis, but that's not the only reaction we look at. What other reactions do we look for? We look for acid-base. Now, for acid-base, what you do is you familiarize yourself with an acid-base chart, like the one posted on Piazza, the one in the classroom here. And most of the acid-base reactions you consider are proton, donor proton acceptor reactions, which are called what?
Bronsted-Lowry.
Bronsted-Lowry. And so we look, well, is potassium ion a good proton donor? No. Is there an H to donate? No. Is it a good proton acceptor?
No.
Potassium K plus an H plus makes a KH2 plus. Is that a good one? No. So as far as Bronsted goes, nothing. Now we haven't talked about Lewis, at least in my class in Chem 1A. We haven't talked about Lewis. But potassium ions aren't that great of a Lewis acid. They really aren't considered. We'll talk more about Lewis acids in chapter 24. We'd have to consider Bronsted, we'd have to consider Lewis, and then it seems, okay, so nothing. Seems like it's unreactive so far with metathesis, unreactive with acid-base, and we have one last category to go with, and that is redox. And so if you're familiar with the redox chart, where does potassium ion sit on the redox chart?
Very.
Well, actually, we could take a look, because the redox chart here from your book, this redox chart is actually from chapter 21 of your book. I just copied this from your book, chapter 21. You can see it there, but here's where potassium ion sits in the redox chart, which means good reducing agent. Well, this is it. Good reducing agents are electron rich or electron poor.
Rich.
Electron rich. So potassium ions are electron rich. They don't mind giving up another electron to go to K2 plus.
Oh, no, that's not true.
That's a good reducer. Good reducers give up electrons, right? Is it? No. No. That means, is potassium ion a good oxidizer? That is, potassium ions love to get electrons to form potassium metal. Yes? No. So if you aren't that familiar with the redox chart, you're going to get familiar with the redox chart because you're going to be looking at this. And what we're looking at are two things. What are the two things you need to memorize from the redox chart? The strongest oxidizer and the strongest reducer. What is the strongest oxidizer on the chart? F2, fluorine. This is the strongest oxidizer. You know, we have, look at the company that fluorine's in. Fluorine, ozone. Do you mind inhaling ozone? No, you would hate it because it would burn, right? And so hydrogen peroxide. Do you like to drink hydrogen peroxide? No. Just like you wouldn't want to inhale fluorine. Definitely would not want to inhale fluorine. In fact, fluorine is so violent, it can catch, you guys remember? It can catch what on fire? Well, fluorine is so powerful of an oxidizer, it can catch. Well, you guys don't remember? I'm talking to the Chem 1A students here.
So,
But.
like, you have like a leak, and then like,
Okay, yeah, the leak, but you know, it could catch, under the right conditions, it could catch stainless steel on fire, which is impressive, you know. Fluorine, actually, just to give you an idea, what's the fluorine chemist handshake? You guys remember the fluorine chemist handshake? Right. Actually, this is pretty. And then this is the retired fluorine chemist handshake because they can't do any more chemistry. As things blow up, you know, with powerful oxidizers, right? And so you got to remember, fluorine is nasty stuff. In fact, you know, I used to work a lot with fluorine, and so I was always looking for stuff regarding fluorine. And so the Army was doing, I saw there's a published report by the U.S. Army, 1950s. They asked for a group of volunteers to take a bottle and a cap and walk into a fluorine cloud as deeply as they could and then seal it and then run out, you know, just to see what the human body could withstand in terms of fluorine. It's like walking into a chlorine cloud. You wouldn't want to walk into a chlorine cloud very far, right? But yeah, interesting. And so that was an interesting study. And that because I heard all the stuff, you know, because when I started fluorine chemistry, you know, everybody told me how dangerous it was. And so I heard about all this. And so after I read that, then I was a little bit relieved, like I'm not going to, you know, be engulfed in flames. It depends on the concentration. Those are very low concentrations of fluorine. Otherwise, they would have died, right? At high concentrations of fluorine. But you could die at high concentrations of anything, right? Like, that's what the whole thing about chemical risk is, because even water can be toxic, right? At high enough concentrations. You know, I was reading that somebody on a radio contest died from drinking too much water. It was like a contest to see who could drink the most water. Did you hear about that in Northern California? Yeah. It's pretty sad. Yeah. And so there's a risk with everything, right? This fluorine has a very high risk, and so you need to be careful with that. And so fluorine is one. What's the other one you have to memorize? Lithium, right? Lithium's at the opposite end. Lithium's a very reactive metal. And actually, you know, lithium is the most powerful, what we call reducer. Fluorine's the most powerful oxidizer. Reducers give up electrons, oxidizers accept electrons. And so if fluorine's at the top, where's potassium? Is it on the oxidizer side or the reducer side? Because you see there's a conjugate relationship here. You know what a conjugate relationship is? Somebody remind me what a conjugate relationship is.
Strong acid.
Yeah, strong acid produces a weak conjugate base, right? It has to. Because a strong acid gives up protons easily. Strong bases grab protons. Right? And so if a strong acid produces a strong base, it can't be so. And so the same thing, if lithium loses electrons easily, that means lithium plus doesn't gain them easily. And so a strong reducer produces a weak oxidizer. That's the conjugate relationship. And so we don't need two tables. We just have one table because they're all conjugate relationships. And so if we have lithium plus means it's well, this is at the bottom. This means it's the weakest oxidizer. What's the second weakest oxidizer? Potassium ion. So when we think about potassium ions, I don't think much for redox. Whereas if I'm thinking potassium metal, then that's something else. Because potassium metal is a conjugate of potassium ion, which is going to be a very powerful reducer. And potassium, in fact, is extremely violent reducer. It reacts with air easily. It reacts with water easily. Some people I know were able to get a little stick of potassium, I think about 200 grams, and then threw it into the faculty pool at UCSB, created a huge explosion, just big flash, and the wave that came up, or the spout of water that came up was like, I think 20 to 30 feet high. It was impressive, just from a little bit of potassium. And so it's pretty violent. Have you guys seen the Army disposal of sodium? I know a lot of you have, but not everybody. Do you want to see it again? I don't want to bore you with repetition. But repetition is good. This is on. I wonder if there's something equally as violent for fluorine. So I'm going to look. Okay. This is, again, the U.S. Army here, disposed of sodium metal. Wow, is the audio not working? Well, you really need to hear the audio on this, because we just put on this. Thought they fixed all the. All right, I guess we don't have audio, but you can see there's a 50-gallon drum of sodium metal going into a lake in Northern California. It's hard to see. But that's just sodium reacting with water. That's what our potassium looked like, but on a much smaller scale. And these are huge cliffs here. Well, take a look at it, because it's not the same without hearing the audio. So that's just an example of how reactive this is, and that sodium here. Sodium is very reactive. Actually, calcium, potassium is much more reactive. Lithium is the oddball here, because normally you'd expect, as far as ionization energies go, potassium would have a lower or higher ionization than sodium. Lower. And why is that?
It's bigger.
It's bigger. Good. Yeah. It's bigger. So the bigger the atom is, the easier it is to strip the electron, the better reducer it should be. But lithium is very small. And so lithium is out of place. Do you know why it's out of place?
It's stability.
Right, it's stability. The stability of lithium ions in water. Wow, Arthur, you remember lots of stuff. It's good. But here, lithium's a bit odd. And so lithium isn't that violent. When you react it with water, it's not like sodium or potassium. It doesn't have these big explosions. It reacts more slowly. But in the long run, that slower reaction generates more energy, because even though it reacts slower, it's harder to pluck the electron off lithium. It's such a small atom, right? And so it's harder to pluck off, but the stability of what we call the hydrated lithium ions, or the solvated lithium ions, changes it. And so we look at, in chemical reactivity, we look at a whole bunch of different factors in terms of chemical reactivity, and we're going to be looking at these this semester. And so, it's not as violent, it's not as intense, but it would generate the most energy thermodynamically. And this is why it's here. And so it's a bit odd. Everybody wonders why lithium Why lithium? Why not potassium? What do you think of cesium? Would cesium be more violent or less violent? You'd expect cesium to be more violent, right? In fact, cesium is extremely violent, the worst of the bunch, basically, in terms of reactivity. Not only that, it has a very low melting point. Cesium will melt in your hand. You'd never want to put cesium in your hand, right? But if you held like a sealed vial of it or container of it, it would melt as you're holding it, just from body heat. And the thing is, what do you think reacts faster? Liquids or solids react faster? Liquids, for sure. And I learned that. I learned that in an explosion that I had in the lab. I was working with some sodium metal, chunks of sodium metal reacting with some alcohol. And this was dry alcohol. There was no water around. Otherwise, you'd see that kind of reaction. But alcohol, sodium reacts a lot slower with than water. So I was reacting this, and I had to do this in something called a dry box, where there's no oxygen and no water. Otherwise, sodium would react with the oxygen and the water. And so it was a dry box. In the dry box, usually if you're doing kind of violent reactions, you want to have an ice bath, right? To have nearby. An ice bath to cool it down because temperature will slow down the reaction. I couldn't have an ice bath, and then I didn't want to put dry ice acetone in there. Dry ice acetone is good too, and it's super cold. And I should have, but I was too lazy to get the dry ice and the acetone. And so instead, I just got a big aluminum plate, and I thought, okay, I'll just put it on the aluminum plate and let the heat dissipate. Right? Aluminum is a good thermal conductor. And so I did that, and so I'm chopping up the sodium to get it to react faster because initially it reacts slow, and then it's starting to react faster and faster. So I put it on the aluminum plate and trying to cool it down a little bit, and then all of a sudden it just went exponential. That's how reactions go. They go like they're nonlinear, and all of a sudden the temperature increased a bit, and then the sodium melted, and boom, it exploded. Fortunately, it was in the dry box, so the dry box was able to contain the explosion. But everybody on the floor ran to see if I was okay. It was okay. And so that was temperature. Temperature is, and that's kinetics. So we're going to talk about kinetics later, because they say there's an old rule of thumb, if you've ever heard it. For every 10 degrees C temperature increase, the rate of the reaction doubles. Have you heard that? That comes from cooking, though. Not for every reaction that holds true, but for cooking, it pretty much is okay. You'll increase the cooking time. Cooking speed, decrease the cooking time, by half by a 10 degrees C temperature increase. Well, anyway, getting back to this. So potassium is pretty unreactive, potassium ions, right? In terms of our reactions. Potassium participates in these sodium ion channels or whatever, and so they'll have an impact on biological systems for sure. But sulfide, what about sulfide? Well, sulfide's a lot more reactive, Sulfides are insoluble with what? Not group 1. Everything except group 1, group 2, and ammonium. And so they react with almost any cation, except for group 1, group 2, and ammonium. Right? And so these are much more reactive in terms of metathesis. As far as acid-base goes, you should know something about sulfide. You know the 7 strong acids, right? How many strong bases do you know? More than 7? Less than 7?
Less than 7.
What are the strong bases? Somebody tell me the strong bases. Hydroxide. Not just any hydroxide. For example, is magnesium hydroxide a strong base?
No.
Why not? Why is magnesium hydroxide not a strong base? It's insoluble, right? And so this is why you can drink this stuff, magnesium hydroxide, milk of magnesia, right, without killing yourself. Whereas if you tried to drink sodium hydroxide, would you survive? Probably not, but, right? Sodium hydroxide, drain cleaner, lye, is a strong base. It's solid. So what we say, the strong bases are not hydroxide. The strong bases are soluble hydroxides. What are the soluble hydroxides? Group 1, calcium, strontium, and barium. Those are the strong bases. Is that it? Are there bases stronger than those?
Yes.
Yes. What? Like what?
Amide.
Amide. Amide's the strongest base on our acid-base chart here, right? Amide's the strongest base on this acid-base chart. This acid-base chart is wrong. I corrected it here. This is old data. Even though this is copyright 1998, you never changed it. And so sulfide is in the wrong position here. But our chart has it in the correct position. Our chart does not have amide as the strongest base. You know, do you know what this is called? Methide. Methane methide. Hydrogen hydride. This is oxide. Here's amide. And then what's this?
Sulfide.
Sulfide. And hydrogen. So automatically when I see sulfide, I think strong base, reacts with lots of metals, ions, and metathesis. Right? And so it's quite reactive chemically, sulfide is, for sure. And so it's a powerful base. These would be the soluble sulfides, of course. You know, the insoluble sulfides aren't. What are the soluble sulfides? Group 1 and group 2 and ammonium, like we just said. This is a little bit of repetition. The insoluble sulfides like iron 3 sulfide, it's not a strong base. That kind of thing. What about redox? Well, does sulfide occur on your redox chart? Here. No. It doesn't. But sulfide, do you know, what would your guess be? Sulfide electron rich or electron poor? Electron rich. And then we think, you know, what's sulfide similar to in terms of family? Oxide. Sulfide and oxide, right? Is oxide a great reducer? No. And so what would you expect? Sulfide to be the same as oxide, worse than oxide, or better than oxide as a reducer? I'd expect it to be better. Why? The size. What do you know about the size? It's larger than oxide, right? And so sulfide's bigger. Bigger is going to mean easier to strip the electrons off. And so sulfide would be a better reducer than oxide. Now, how much better is it? It turns out that sulfide is quite a bit better. But why doesn't it occur on our redox chart here? Well, it doesn't occur on this redox chart, but in Appendix D in our book, and Mastering Chem, I was asked about that. You know what? I forgot to set this up, and I still haven't set it up. I'm not requiring Mastering Chem this semester, but I'll set it up with the tutorials so you can access it. But I like Mastering Chem. It has the e-text here that we can take a look at. It has practice quizzes that you can work on. It has reviews. And so Mastering Chem is a good resource. I'm just not doing the homework. That's it. All right, so let's go to Appendix D. Ground state electron configurations, thermodynamic data. Equilibrium constants, which we're spending a lot of time on. Formation constants. Redox. All right, so here we see fluorine. This redox chart is much more comprehensive than the one in chapter 21. So we see a lot, you know, for example, OF2, which we don't see. Ozone we saw. This one's an unusual sulfur-containing anion. Look at this. This is odd. What's odd about this?
Two oxidation states.
Yeah. Silver is a fixed charge at +1. You'd need an awful powerful oxidizer to strip another electron off that. Right? But it can be done. You know, a lot of people try to generate unusual oxidation states. You know, one of the reasons why I was using fluorine was to generate iron +4. Right? Iron +4 is an unusual oxidation state of iron to make some exotic compounds. That's the reason why. And so trying to generate unusual oxidation states. Well, that certainly is one there. Some common oxidizers like this, MnO4-, what's that called? Permanganate. Lead-4 is the decent one, sulfate. Lead-4 and sulfate, this is the one in car batteries here. Gold-3, you get oxidizer. This is different. What's the difference between these? I see permanganate twice. Why? Why? Why do I see permanganate twice? Could it be a mistake? Sometimes I make mistakes and write it twice. Both of them have acid. Which one is the stronger oxidizer? The one that's on top. Right? And so whenever you have permanganate, how is it going to react? It's going to react in the way that the strongest. And so which permanganate is stronger? This one. So it should react like this, right? What does it form? The difference is the product it forms. You know, under certain conditions, we form different products. And sometimes we have partial reaction. We don't have complete reaction. And so it doesn't go all the way like you'd expect. You know? And so all we're trying to do is get familiar with typical products. You know? Oftentimes, what you do in some redox is just mix it together and see what happens. That's skeleton redox, right? Mix it together, see what happens. Because little factors like temperature, pressure, etc., changes what you can expect for products. You know? And it can get quite complicated. So we kind of just need some kind of reference point, some anchor point to figure these things out. Well, let's go on. Is sulfide an oxidizer? Does it want electrons? No, it wants to. It wants to be a reducer. So maybe I'm starting at the wrong place. Let's start at, what's the most powerful reducer? Lithium. So let's start at lithium. The metals are all going to be good reducers, especially group 1 metals and group 2 metals. As you'd expect, metals should be electron rich. Zinc, neon, tin, hydrogen sulfide. Hydrogen sulfide is a moderate reducer. Hydrogen sulfide is, what's the oxidation state of hydrogen? +1. What's the oxidation state of sulfur? -2. So here we see it's a moderate reducer. What happens is the -2 sulfur goes to just elemental sulfur, loses 2 electrons, right? All right, this doesn't have sulfide. And so the closest species would be hydrogen sulfide, and we can see it's going to be a decent reducer. Did anything happen to hydrogen in this? Let's take a look. Where was it again? Did anything happen to hydrogen? No, because hydrogen went from +1 to +1. Do you guys remember the how to assign oxidation states? Yeah, if not, you need to review it. Do you know the definition of oxidation state? What's the difference between oxidation state and formal charge?
Ionic character and covalent character.
Okay. Does everybody know the difference between oxidation state and formal charge? If not, go back in your book and take a look at the difference. You need to know the difference between oxidation state and formal charge, what those numbers tell you. What does the number mean? So for example, if I look at, let's just look at H2S. If I look at H2S, what are the formal charges? 0, 0, 0. So what does that mean? 0. We circle the formal charges. What does that mean? Think about what it means, and you got to explain. You got to explain to me in a paragraph what that means. Okay. Let's look at the oxidation state. Formal charges I circle. Oxidation states I put in parentheses. What are the oxidation states? We do hydrogen first. And so what does oxidation state mean? Tell me in a paragraph. And then what is the difference between oxidation state and formal charge? For example, why is sulfur -2 and 0? Okay, that's fine, but you know, if you know, that's good. If you don't know, you need to know. Because we use these numbers, and if you don't know the definition of these numbers, then do it now, you know. Go back and review here. If everybody knows, that's fine, that's good. But we're going to be using these numbers a lot. This is in chapter 3 of your book, Oxidation States, and formal charges in chapter, I forgot, 11, 10? Right. Of your book.
The current book we have right now, or like the Chem 1A.
Chem 1A. This is a Chem 1A, or Chem 1A stuff. This is a Chem 1A review, the first 2 days. The Chem 1A stuff that you need to know for Chem 1B. Like bonding. For example, you need to know this. What's the difference between valence bond theory and molecular orbital theory? Can you tell me how each is defined? And
Just the configuration of the electrons. MO has bonding and anti-bonding.
yeah, those are characteristics, two characteristics of it, but what are they? I mean, you know, how would you define them?
Molecular orbital theory, orbitals share the entire molecule, not just a single atom. And valence bond theory says that these orbitals can be generated for a single atom and hybridizing.
Okay. Yeah, those are good characteristics of the two. But essentially, what's the difference? Why do we need two? You know, why do we need two ways of doing it? I mean, or are they the same? Are they the same thing?
MO is more accurate. Valence is quantum theory, light.
Okay, yeah, this is one way of putting it. Valence bond theory, you know, there are two ways of describing a bond. Valence bond theory describes a bond as overlapping atomic orbitals, and so retains atomic orbitals. And so, whereas molecular orbital theory pretty much gets rid of the atomic orbitals and replaces those with molecular orbitals. And so it turns out molecular orbital theory is the full quantum mechanical approach to bonding, whereas valence bond is a light version. You know, valence bond, the reason, well, why do we retain the light version? Why don't we just go with the full version? It's easier, right? We can do it on paper easily. And it's fast. And is it accurate, though?
Not always.
No. What's the big failure of valence bond theory? Oxygen. Okay, good. You guys. Fresh. Still fresh in your memory. If it's not fresh, you know, we have time, so start reviewing this week, okay? All right, so this is a more comprehensive redox chart, and there's even more comprehensive redox charts, of course. And so just because it isn't on the redox chart that I hand out, it might be on this redox chart. And just because it isn't on this redox chart, it might be on another redox chart. But we get an idea, you know, we get an idea of, like, for example, did we need a redox chart to predict that sulfide is going to be a reducer? No. Okay, so sulfides is actually quite reactive, right? It can react in metathesis, acid-base, and redox. And as far as the strongest, in terms of reactivity, you know, I guess all of it stands out. This can precipitate with a lot of things, right? But one of the things that's very tricky is this. And this is why I brought this up. Now, let's take a look at this reaction here. Potassium sulfide and acetic acid. Well, potassium sulfide is K2S, right? And acetic acid is what? I don't know why, but a lot of students in my Chem 1A class last semester wrote acetic acid as H4C2O2. C2, wait, yeah. I don't like this, actually. I don't like this. Do you know why I don't like this? Because it makes 4 hydrogens the same, the equivalent. Are these 4 hydrogens equivalent?
No.
No, there's only 1 acidic hydrogen and 3 non-acidic. And so this, you're losing a lot of information if you write it like this. You know, this is not a good way to write it. The reason is because, I mean, when you look at the Lewis structure, only one of these hydrogens is acidic, and which one is it? The one on the bottom of this. These are totally non-acidic here. This is like trying to make methane an acid. Is methane an acid? No. And so we need to keep those separate. In fact, another way that people write acetic acid, which is even better, is the condensed structural formula. This is the condensed structural formula. Just flip. There's your acidic hydrogen here. And so you'll often see it like this, CH3COOH. So we got this reaction. This just looks like a double replacement, AB plus CD. What forms? Potassium acetate and hydrogen sulfide. Hydrogen sulfide is AQ or gas. The maximum, you know what solubility is? What's the definition of solubility again? Solubility is defined as, there are 2 definitions. There's a qualitative definition of solubility and the quantitative definition. Qualitative definition is, if it's soluble, it dissolves in water, right? What's the quantitative? Quantitative is the maximum amount that will dissolve. And the maximum amount of H2S that dissolves in water is 0.1 moles per liter. And so the maximum concentration you can get of H2S in water is 0.1 molar. Anything in excess of that will bubble out. And so this is going to generate gas, you know, the amount of H2S we're generating here. H2S gas, is it good stuff to inhale? No. I mean, some oil worker in Ventura died from H2S inhalation, well, less than 10 years ago, you know. So it still happens. Let's balance this. Yeah. Well, what's the driving force? We have 2 driving forces here, you know, that we can think of. We're going from stronger acid because acetic acid is a stronger acid than H2S to weaker acid. And so we could just look at the acid chart there. H2S is a stronger acid than acetic. Is that correct? Did I get that right? Well, let's take a look at my acid chart here. Maybe I didn't. Here's H2S. Where's acetic acid? Here's acetic acid. H2S is here. Acetic acid is here. Which one's? Oops, this is formic acid. This is acetic acid. Which one's a stronger acid? Wait, this is wrong. This is not a driving force. We got this wrong.
It is.
Oh, it is. Oh, it is. I don't know what I'm thinking. Oops. So we're going from stronger acid to weaker acid, WA. It doesn't have to be a strong acid, just stronger, right? That's it. And gas formation. Since H2S has limited solubility in water. That's why. All right, this is what we call the CE. What about the IE?
Break it down.
Yeah, this potassium and... Right. So we have 2 potassiums and a sulfide, right? And so let me stop here because I'm going to put a little asterisk on this. What about, well, put a little asterisk here. And sulfide. What about acetic acid? You leave it.
Oh, so
Potassium acetate?
Yeah.
Break it down. Make sure it's balanced. If it's not balanced, you know, a lot of people forget. They'll write 2 potassiums with 1 acetate. That's wrong. 2 potassiums and 2 acetates. No, I'm leaving off AQ from now on. I don't want to write it. And so if it's blank, it's AQ. If it's not blank, then it's a solid, liquid, or gas. You need to write it down.
If we had a test where we had the balance information, we leave off AQ.
No, on a test you can omit AQ, but you cannot omit solid, liquid, gas. All right. The reason I wrote sulfide with an asterisk here is you need to know something about strong bases. Strong bases are also strong electrolytes. Strong bases are strong electrolytes. Strong electrolytes do what in water? They dissociate completely. So what does sulfide dissociate completely into? What would sulfide dissociate into? Nothing. I mean, what could you dissociate? And so we have to get away. Remember, bases do not dissociate in water. Bases hydrolyze in water. And so that has to be drilled down. So strong bases hydrolyze in water, meaning this. This is the wrong thing. You know, what happens is that sulfide is too strong of a base to exist in water. All the strong bases here are too strong to exist in water. The only base that can exist stably in water, the only strong base that can exist stably in water is hydroxide. Do you see? That's why there's these lines here. What's the strongest acid that can exist in water? What's the strongest acid that can exist in water? Hydronium. Are you going to find any HCl molecules in water? No, because they're all going to be, hydrolyzed to H3O plus or H plus. For acids, we could say dissociate or hydrolyze. For bases, we got to say hydrolyze. And so all these bases, you're never going to find. Can you make a 1 molar methide solution? Impossible. Can you make a 1 molar hydride solution? Impossible. 1 molar oxide solution? 1 molar amide solution? 1 molar sulfide solution? Impossible. All these are going to do what in water? They're going to hydrolyze. So if you tried to make a 1 molar methide solution, the methide would attack water and form hydroxide. So your 1 molar methide solution ends up being a 1 molar hydroxide solution. Right? This is the leveling effect of strong acids. I talked about this yesterday, I think, mentioned it. What's the strongest acid? What's this called? Perchloric acid. If you try to make a 1 molar perchloric acid solution, you know what you're going to get? You're going to get 1 molar hydronium, because all the H plus is going to dissociate. If you try to make a 1 molar HCl solution, you wouldn't end up with 1 molar HCl, you'd end up with 1 molar hydronium. And so these 2 acids produce exactly the same amount of hydronium, thus the leveling effect. The leveling effect occurs for strong bases as well. All strong bases are are going to go to hydroxide. So all strong bases in water are the same strength. So what happens is sulfide reacts with water to form hydroxide. Now, when I say this is qualitative. In Chem 1B, we're going to get more quantitative than this. And so sulfide will hydrolyze water to form what? This is our base, and this is our acid. This is a proton donor. We form HS minus plus OH minus. This goes 100% strong base, right? And so we don't end up with sulfide, we end up with hydroxide and hydrogen sulfide. Well, hydrogen sulfide turns out to be an amphoteric species, and it's a more stronger base than it is an acid. And so, you know, the basicity of this, we're going to do some calculations later to figure out the impact of HS minus on the basicity of hydroxide later on this semester. Okay. But for right now, we want to be able to do these qualitative in our head, right, so that when we get to the calculations, we kind of know what to expect. Okay. And so here, sulfide does not exist in water. And so that's why I put the little asterisk there. We aren't going to find sulfide in water because we know sulfide is too powerful of a base to exist in water.
So we write that.
No. So this is what we do. In Chem 1A, we avoid this kind of scenario where you write the wrong answer following the steps that we teach you to do, right? But in Chem 1B, you know, we don't want to... we don't want to we don't want to keep you in a protected environment at all times. A protected environment is where you only get the questions that work out nicely, right, and aren't too messy. We want to open up the environment so you get questions that are more right. And so here, so are you going to know? But you should know. So it's not going to have any impact because HS minus will react in the same way. Rather than having sulfide attack this, HS minus is plenty strong enough a base to attack this acid to form H2S. And so we'd still end up with the same product.
So we stop.
What?
So do we stop where the...
So this is what we would do here in the NIE. You could do either. If you want to be totally proper about this, you would do this, right? And figure it all out. But for us, we're just going to do this. We're just going to say sulfide plus 2 yields 2 acetates plus H2S. And we'll put a little asterisk here. Because I haven't talked about acid base. We try to, I still try to keep things clean. And so let's talk about acid base reactions now. The next part of this. How late do we go till?
55.
55? So acid base is part 2 of this. I haven't updated these since 2011, even though it says 2015. I need to correct, like, for example, I need to correct the other ones. I noticed there are 2 mistakes on the part 1 point. But what's Arrhenius? What is the difference between Arrhenius, Bronsted, Lauer, and Lewis? Oh, first off, what are these 3? These 3 are considered the 3 ways to define what an acid and base are. Why do we need 3 ways? One is a better? Well, why don't I just pick the best one and then eliminate the other 2? Okay, well, one of them will eliminate right off, the Arrhenius. We're going to eliminate that because it's too narrow of a definition. You know, this is a kind of historical. Arrhenius came along and said all acids are like this, all bases are like this, and then they found other acids that aren't, right? And so Arrhenius acids are H plus AQ, Arrhenius bases are OH minus AQ. We'll eliminate that. Then Bronsted and Lowry came along, redefined it, and then finally there are acids and bases that were missed by Bronsted and Lowry. And so Lewis came along and gave an even more general definition. And which one is the most general definition? Lewis, right? And so we can eliminate 1 and 2. We'll eliminate 1, but we don't eliminate 2. And Adrian, why not? I mean, you had the answer earlier. Or was it? Or Andy, was it? 2 is the easiest. 2 is for sure is the easiest. So we don't eliminate 2. We keep it. And so let's look at Bronsted-Lowry. This is the easiest. The Bronsted-Lowry acid-base reactions, we just transfer 1 proton from the acid to the base. Determine the driving force, determine the further reaction force. So the method, we inventory the solution, which just means figuring out what are the major species in solution using solubility and electrolyte properties. 2, we determine the strongest acid and the strongest base present. 3, we transfer a single. You just do this one at a time. Because if you think about it, let's say you have a diprotic acid. Do 2 bases come and attack it in the exact same instant of time? I mean, they have it timed with a stopwatch or something. So at T10, they both attack it and pluck both protons off at the exact same time? What do you think? No, it happens one at a time, right? And so this is the way we're going to approach it. This is different than this. This is what we call dibasic base. A dibasic base can accept 2 protons, right? In metathesis, we always react to completion. And so if we have a dibasic base, then we need 2 protons to neutralize that. If we have diprotic acid, then we need 2 hydroxides to neutralize that, right? And so metathesis, we react to completion. If we have a triprotic base, we're going to react all 3 protons. But in Bronsted-Lowry acid base, this type, we only do 1 at a time. Otherwise, we can get screwed up and go too far. Determine driving force, if any. The driving force for Bronsted acid-base reaction is very simple. Stronger acid to weaker acid. Because of the conjugate relationship, the following must be true. Stronger base to weaker base. Right. And then we repeat. You know, for example, if we had a diprotic acid, we do the first proton and then repeat. Will further reaction take place? We determine that. And then repeat, you know, with a triprotic. So let's look at an example. Phosphoric acid and sodium hydroxide. I don't have much time, so I'm going to write this. All right, what's the formula for phosphoric acid? H3PO4. This is a triprotic acid. Sodium hydroxide? Anyway. Well, there's some overlap because this is a metathesis reaction. It follows the AB plus CD pattern, right? And so in the metathesis approach, what did I say? Repeat what I said. In metathesis, if it's triprotic acid, we're going to react all 3. And we'll form what? Water and? Yeah. Water and sodium phosphate. What's the formula for sodium phosphate? Na3PO4. And so let's balance this. We need 3 and 3 H2Os. What's the driving force for this? Okay, yeah, we're forming a liquid. That's also a driving force. but it's easier to memorize fewer driving forces than more, because forming a liquid is just a subcategory of stronger to weaker acid. So we just use stronger to weaker because it's more general and it captures this. So we don't need to memorize formation of a liquid, although that's one that's used in Chem 4 a lot. We're going from stronger acid to weaker acid. Weaker acid, water. Stronger acid. Water is interesting because water is amphoteric, but in this case, water is the acid. Why is water the acid in this case?
Because it's stronger.
No, it's because of, if you reverse this reaction, what happens? Water is the, no, water is the proton donor, right? Do you see water is going to be the proton donor, therefore if you reverse this reaction, it's the acid. And so this is why I know it's the acid. Otherwise, I don't know. I have to always reverse it to see how is it behaving. Is it behaving as an acid or is it behaving as a base? Because I can't tell until I see the reaction. And so there's no way to define it until you actually see it. Right? And so in this way, I know that water is going to be the acid. That's a metathesis approach, etc. You know, do we ionize phosphoric acid? Yes or no? No, because it's a weak acid. All right, for acid-base, we approach this differently. First, we inventory the solution. And so H3PO4, AQ consists mostly of H3PO4. Sodium hydroxide, AQ, consists mostly of sodium ions and hydroxide ions. And there's one more thing present. Water. The solvent can react because water is amphoteric. Water can either react as an acid or base, so we have to consider it. Well, is phosphoric acid, well, that's an acid, but could it also act as a base? Is phosphoric acid amphoteric? No. No, it's not. Sodium ions. Neutral. I'll just write N. Right? They're not going to do anything. Hydroxide. It's a base, but could it react as an acid?
No.
Can it react as an acid? Yes, it can. Yes, it can, because yeah, if it loses a proton, what does it form?
Oxide.
Oxide, right. Not only that, it's on your chart. You should be able to see this here. Hydroxide loses a proton to form oxide. Hydroxide is one of the worst acids on the chart, but we'll put it up there in case, because it can react. Water is both. It occurs on both sides of the acid-base chart. So it's acid-base. And so we have three acids. Out of these three acids, which one's the strongest? Phosphoric. We have two bases. Which base is strongest? Hydroxide. And so we ignore the others. If you're going to have a reaction, you're going to have a reaction between the two strongest reactants, right? That's the most probable reaction. Everything else is not as probable. Okay. What's the next step? Proton transfer. How many protons do we transfer? One. And so what forms?
H2PO4.
Is there a driving force? Okay, we're going from stronger acid, hopefully, to weaker acid. Now, which one is the acid? On the okay, the acid on the left is phosphoric acid. Which one is the acid on the right?
Water.
Water? Look at H2PO4 minus is a stronger acid than water, so shouldn't it be H2PO4 minus?
No, when you reverse the reaction, the water.
Yes, do you see that? I don't know based on the chart, even though H2PO4 minus is a better acid than water, both of these are amphoteric. We don't know which one is which until we see the reaction. And so the reaction tells me that water is the acid. Even though H2PO4 minus may be a stronger acid, it's not the acid in this reaction. This is the acid. Did everybody get that? Water is the acid because who donates the proton going backwards? Water. And therefore, going backwards, water is the acid. This is the base because water loses the proton. H2PO4 minus gains the proton, irregardless of what the chart says. Does that make sense? So we do that, and we see that. Is there a driving force? Yeah. Phosphoric acid is much stronger acid, and the bases follow. Hydroxide is a much stronger base than H2PO4 minus. H2PO4 minus is amphoteric. It could go either way, right? Occurs on both sides of the chart. So we got reaction here. It depends if we have excess hydroxide present. You know, this is an option. If excess hydroxide is present, then we could have further reaction. If excess hydroxide present, then what do we have left over? Well, let's inventory it. We have H2PO4 minus, water, and excess hydroxide. H2PO4 minus is amphoteric, water is amphoteric, hydroxide is amphoteric. And so we have 3 acids and 3 bases. Which is the strongest acid?
Biphosphate.
Dihydrogen phosphate. Which is the strongest base?
Hydroxide.
Hydroxide. And so we could have a second step to this. H2PO4 minus plus another hydroxide gives us what? Monohydrogen phosphate and water. Now, this is the acid. Which is the acid on the product side? Water again. And so we're going from stronger acid to weaker acid. So we got driving force here. If still we have excess hydroxide, then we'll just inventory what we have left over. We have HPO4 2 minus plus water plus excess hydroxide. And so again, we have 3 amphoteric species. Which one's the strongest acid? HPO4 2 minus. The strongest base will be the excess hydroxide. So we get HPO4 2 minus plus hydroxide gives us PO4 3 minus phosphate and water. And we go from this acid to, again, water. So we're going from stronger acid to weaker acid. So there's driving force here. If still there's excess hydroxide present, if we still have excess hydroxide present, then we got what's left over? Phosphate, water, and hydroxide. And so which one's the strongest acid?
Water.
Well, actually, phosphate. Is it amphoteric? It's a base. Water?
Amphoteric.
Amphoteric? Amphoteric. So which one's the stronger acid? Water. Which one's the stronger base? Hydroxide. And so the reaction will be water plus hydroxide yield hydroxide and water. So did anything happen? So we stop here, right? This is no reaction in R, basically. So that's the end. Right? Do you see this repetition? Repeat? If we have access. So that's an example of how we approach the Bronsted acid-base reaction and how it differs from metathesis. Here's another example that you could do. Solutions of sodium monohydrogen phosphate and potassium hydrogen sulfate are mixed. Another example of a Bronsted. Solid sodium amide is mixed with water. Let's see. So you can work on those examples at home. See what you get. Well, you know, again, with our two-pronged approach, we have a bit of memorization. You know, you should memorize the strong acids. You should memorize some of the strong bases so that if you see it, it automatically registers. Oh, that's a strong base, right? But not only do we want to have the memorization, we also want a little bit of theoretical. And the little bit of theoretical came about, for example, which one do you think is a stronger base? You know, oxide or sulfide? And why? Don't look at that chart. That chart's wrong. We can look at our chart. Sulfide's a stronger base? Why?
It's big.
It's bigger? So if it's bigger, it wants a proton more than if it's smaller?
Oh no. It's really
So did you say which one is a stronger base? Which one's a weaker base? You said sulfide's a stronger base? Well, the data's wrong. The data shows that oxide's a stronger base. Why do you think oxide's a stronger base? Well, think about chemistry. What is chemistry all about? Electrical interactions. A hydrogen is H+. The base is negative. So it's a negative positive interaction. Which one is going to have a stronger attraction for a positive proton? An oxide or a sulfide? Oxide. Why? It's smaller, right? Oxide's smaller. It's going to have a higher charge density. It's going to be more reactive. Therefore, it's a stronger base. And so, how about selenide? Tell me, what do you expect selenide? Stronger base or weaker base?
Weaker.
Weaker. Why?
Big.
It's even bigger. Stronger or weaker than sulfide?
Weaker than salt.
Weaker than sulfide. Stronger or weaker than telluride?
Stronger.
Stronger than telluride. And so what we want to do is we want to do the two-pronged approach. We don't want to just do straight memorization. We also want to do this little bit of theoretical. You guys know about size, right? You know about charge. You know about charge to size density. You know Coulomb's law. And so this is what we call the kind of the what do we call this? Well, we call this the semi-empirical approach, semi-quantitative approach. You know, we aren't applying full quantum theory. You know, we don't always apply full quantum theory to everything we do. Well, we could. We could apply full quantum theory. This is what we're going to do in lab. We're looking at charge densities here. So, for example, if we compare acetic acid with sulfuric acid and look at this is the quantum mechanical calculation of the charge density in this. You guys remember the electrostatic potentials? What does red mean?
Very negative.
Very negative. Blue means very positive. And so if we compare the blue region here, look at the acidic hydrogen. Can you see these are green hydrogens? Green hydrogens, are they very acidic?
No.
No, those are the methyl hydrogens that are written up there. So 3 of these hydrogens are pretty non-acidic. Only one is acidic, this blue one here, in acetic acid. And that's shown here. But compare the blue hydrogen here to the blue hydrogen on sulfuric acid. Do you guys see that?
Yeah.
Sulfuric acid is quite a bit more polar. Now, why is that? So what we do is, okay, acid-base chart, we get familiar with that. We learn the trends, we learn the patterns. You guys are good at patterns, right? You know, what do scientists do typically? Observation, look for patterns. Yeah, and so one of the things we do, we look for these patterns in the acid-base chart. We can do that later. And then, as far as analysis goes, we don't have full quantum mechanical computational software, and so we do this by pencil and paper. We do this by pencil and paper by using Lewis structures. And this is why I went through Lewis structures, because we're going to do a lot with Lewis structures to try to figure out chemical reactivity. And so we do this, and we look at bond strength, bond polarity, bond product stability, these types of things here. And so for sulfuric acid versus acetic acid, why is the proton, the acidic proton on sulfuric acid so much more acidic than an acetic acid? And so let's take a look at the structures here. So we draw the Lewis structure for acetic acid. And the Lewis structure for sulfuric acid. Okay, which one do you want to draw for sulfuric acid?
2 double bonds.
2 double bonds, something like that? This should be 2 double bonds with remember the asterisk?
Yeah.
Why? Because both these double bonds would require what type of pi bond? DP or PD pi bonds. Yeah. Having 2 is already pushing it. Because d orbitals are 90 apart. It should be 109. This is tetrahedral. Okay, tell me why this is much more.
Much less.
Or, excuse me, tell me why this is much more acidic.
Induction effect.
Induction effect. Induction effect. Somebody remind me what the induction effect is.
It's
This is what
the electronegativity of the oxygen pulling inside.
Okay, you both of you guys.
This guy.
In stereo, yeah. Yeah, you almost beat him. Yeah, you actually have this. That's good. Wow, you guys are good. Induction effect. So how would you draw it or show it? You could use the arrows. You guys remember this?
Yeah.
Which one's more electronegative, carbon or oxygen? The reason I'm drawing the arrow like this is because this carbon is not like a normal carbon. What's the normal electronegativity on carbon? 2.4. 2.4. Yeah, 2.4. Something like that. 2.4, 2.5. Whatever. That's a normal electronegative. Is this a normal carbon? No. Why not? Why isn't that? Why would you expect the electronegativity of this to be higher than 2.4 or lower than 2.4? Higher than 2.4. Why?
The top oxygen is pulling the electron from making it.
The carbon. You know, there's a tug of war here. Normally, oxygen wins the tug of war because it's more electronegative, right? But in this case, carbon is going to put up a much bigger fight. And so to show this, it's going to be like this, polarized like this. And this carbon's going to put up a much bigger fight because its electronegativity is not 2.4 anymore. It's actually higher. The reason it's higher is because the other oxygen on the top there, yes. And what's a good way to quantitate this? There's a good way to quantitate this. It's like this. This is fluorine's electronegativity is 4.0. It's the highest, right? Is fluoride's electronegativity 4.0? No. What would you expect? Higher, lower? Much lower than 4.0. Way lower. Way lower than 4.0, right? What about something like this? F plus. Much higher than 4.0. Off the charts, right? And so this carbon, what's a good way to quantitate this or to actually see this is by looking at the formal charge? What's the formal charge on carbon? 0. A much better way of quantitating this is not using formal charge, it's using
Oxidation.
oxidation state. So what's the oxidation state of this carbon? This is something you guys have to, I know you Chem 1A'ers that I had, this is the way we did it, but can anybody else tell me what the oxidation state on this carbon is?
One.
All right, actually, can anybody tell me what the oxidation state on the carbon is? Plus 3? That's right. So the oxidation state's plus 3.
Oh,
What's the oxidation state on this carbon?
minus 3.
-3. Do you guys know how to do that?
Yeah.
I mean, does everybody know how to do this or no? This is a plus 3 carbon. This is a minus 3 carbon. These two carbons are totally different. Do you guys see that? So this one would have a very high electronegativity. This one would have a very low electronegativity. In fact, in organic chemistry, they call these electron pusher groups because they're electron rich. Right? Uh-huh. Now, how do you do that? How you do that is, did anybody look up the definition of oxidation state? Well, what is the definition of oxidation state? Did I ask you guys that yesterday? I asked you that today? You haven't had a chance to look it up yet? Look it up. Tell me what the definition, because we're out of time. Tell me what the definition of oxidation state and tell me what the definition of formal charge is, and then we'll talk about it.